In this video, we're going to look at solving trigonometric equations day 2. So this is on page 2 in your note packet. And so we looked at simplifying some basic expressions. The other day we looked at reciprocal functions and rewriting tangent and cotangent and sines and cosines, and then Pythagorean identities. Today, we're going to look at doing some algebra with the expressions. So in this case, we're going to be looking at factoring. And you may or may not want to rewrite this without the trig functions right away, if that helps you to simplify the look of them to help you see it better. So if you wanted to rewrite this as 2x squared minus 3x plus 1, so you could look at factoring this. And now you can do area model for this, right? So 2x squared minus 3x plus 1. So you would multiply these two together. Well, actually, let's put it in the box first. So you have the 2x squared minus 3x plus 1 here. And then you multiplied the first and the last number together for 2x squared. And then you find the factors of positive 2x squared that add to negative 3x. And so that's going to be a negative 2x and a negative 1x. And then you fill those in the remaining boxes, whichever you want. You can flip these around, that doesn't matter. Then you take a common factor out of this top. So what do they both divide by? Well, they both divide by a 2 and an x. And then you can just fill up the blank spaces. So 2x times 1x will give us 2x squared. And 2x times negative 1 will give us negative 2x. 1x times negative 1 will give us that negative 1x there. And then I always multiply the last numbers together to make sure that they equal that last box too. So negative 1 times negative 1 gives us positive 1. So this expression factors to 2x minus 1 times x minus 1. So then when we go back here, so now we know that this factored to 2x minus 1 times x plus x minus 1. So remember that it wasn't just an x, it was a sine x. So now you need to make sure that you write in the sign again. So this is 2 sine x minus 1 times sine x minus 1. And then that would be factored completely and we would be done. This next one is a difference of squares. So again, if you want to rewrite this without the trig in it, you could look at this as 16 minus x squared. And then you see that both 16 and x are perfect squares. So when you factor this, okay, the square root of 16 is 4, and the square root of x squared is x. So you're going to have 4 and x in both expressions. One is going to be minus x, and one is going to be plus x. And then when you put the trig function back in, that would be 4 minus secant of x, and then 4 plus secant of x. Next ones, now we have cosecant alpha minus cosecant alpha times cosine squared alpha. So again, if you're working on a strategy of getting rid of those trig functions to simplify the look for yourself, you could call cosecant of alpha a. So you have a minus, and then you have cosecant again, which you called a. And now you have a new function, cosine squared of alpha. So then this would be b squared. So now you're looking at factoring this. And in that case, hopefully you see that they both have an a in common. And so you can factor that a out. So when we divide the a out, a divided by a is 1. Negative ab squared. Take out the a is just negative b squared. And then this part is a difference of squares again, just like on that last one. So then we would have our a, and now this is going to end up being 1, since square root of 1 is 1, and then the square root of b squared is b. And then we're going to have a minus and a plus so that those middles cancel out. So then this whole thing factors to, now our a function was cosecant of alpha, and then 1 minus our b was cosine of alpha. So we get, cosecant times 1 minus cosine, 1 plus cosine. Now in D, if you notice, we've got 2 different functions, okay? And so this strategy to just change them to different letters, right, and call this a squared minus b minus 3, well, that's not factorable because these aren't the same variable. And we don't have an a in common or a b in common. So this is why we wanted to look at those Pythagorean identities and know how to rewrite functions, because now we're going to want to rewrite to try to get these in the same, to be the same function, either cosecant or cotangent. Now, we know cosecant is 1 over sine, but that doesn't help us. And so in this case, I would look to the Pythagorean identities because I see a squared function. And so the identity with cosecant is that cotangent squared of beta, and I'm just going to change the variable to beta, plus 1 equals cotangent squared of beta. So what we, equals cosecant squared of beta, my fault. So now what we can do is we can substitute this in place of cosecant. So where we see cosecant squared of beta, we're just going to put in cotangent of beta plus 1. So cosecant squared is cotangent squared of beta plus 1. And then we also still have the minus cotangent of beta minus 3. So now we can just combine our like terms, the 1 and the negative 3. And so we have cotangent squared of beta minus cotangent of beta. And then 1 minus 3 gives us negative 2. Now we have a squared version of the function and a non-squared version, and then a constant. So this can now factor. And so if we rewrote this in a simplified version, if you want to, I'm just going to write it over here. So we would have a squared minus a minus 2. So now this just has a leading coefficient of 1. So we can just find the factors of negative 2 that add to the middle term of negative 1, because we know a times a is the only thing that's going to get us a squared. And the negative 2 and positive 1 is going to get us that negative 1 in the middle. So then if we just use that with our cotangent function, then it's going to be cotangent of beta minus 2 times cotangent of beta plus 1. Example 5, so simplifying by expanding and using identities. And so if we look at this, we see a couple different things happening, right? So hopefully you start to recognize that you have a difference of squares up here. So we have secant plus 1 and secant minus 1. So we know if we were to multiply this out, the middles are going to drop out. Okay, so I'm just going to do it. I'm just going to multiply the whole thing out just so you can see that. And I'll just do it in the box. If you don't need to use the box, that's fine. You can distribute or FOIL, use FOIL method. So secant times secant is going to give us secant squared of x. Secant times 1 is going to give us secant x. Secant times -1 is going to give us negative secant x. And -1 times 1 is going to give us -1. And then we can see that a negative secant and a positive secant cancel. So our top is going to give us secant squared of x minus 1 when we multiply it out. Now, the reason that this is going to be helpful in this case, because secant is the reciprocal of cosine, which doesn't really help us with sine. So that's why when we multiply this out and knowing that this is a difference of squares, so it's going to give us secant squared minus 1, then this top part is now a manipulation of a Pythagorean identity, more than likely. So if you go back to your Pythagorean identities with the secant squared, okay, you have 1 plus tangent squared of x equals secant squared of x. So now we're just going to manipulate this because we want it to say secant minus 1, right? So I'm just going to subtract 1 from over here. So I get tan squared of x equals secant squared of x minus 1. And this is what we have in our function, right? Or in our problem. So now we're just going to replace that with tan squared of x since they're equivalent. So where we see secant squared of x minus 1, we'll put in tan squared of x. So now we have tan squared of x over sine squared of x. And then we know that we can rewrite tangent with sines and cosines. So let's first rewrite this as tan squared x, and then times, I'm going to write it as times 1 over sine squared of x, right? Because we know that with that on the bottom, okay, that's 1 over sine squared. So I'm just going to rewrite it like this, knowing that I'm going to rewrite tangent squared. So now tangent squared is equal to sine squared over cosine squared. So if I rewrite tangent, that's going to be sine squared over cosine squared. And then we have times 1 over sine squared. And then we see that we have a common factor of sine squared on top and bottom. So those will cancel or divide to 1. And then we get 1 over cosine squared, which is a reciprocal. And the reciprocal of cosine is secant. So this is secant squared of x. Obviously, there's going to be other ways to do that. So if you tackled it a different way and came up with the same answer, that's fine. All right, example 6. So simplify this expression. So one new thing that we're seeing in here is that we have a minus. So we've got 2 functions here, or 2 expressions, and then we have them separated by a subtraction instead of them just being divided by each other. So in this case, one of your strategies is to get them to be one fraction. So get common denominators and then go from there. In this case, then it tells us we're going to use a Pythagorean identity. So let's get common denominators. So we see that the denominator on this side is 1 minus sine x, and we see that the denominator on this side is cosine x. So we're going to multiply this side by cosine x over cosine x. Remember, you got to multiply top and bottom. And then we're going to multiply this side by 1 minus sine x. To get those common denominators. So on the left side, we're going to get cosine squared of x on the top And then on the bottom, now I'm just going to leave this. I'm not going to multiply this out, okay? I'm going to leave it as 1 minus sine x. And this is because I know where this is headed, and multiplying it out isn't going to be helpful to you, okay? And most of the time, it's not going to be helpful to you to multiply out the denominators, okay? Numerators, yes, because you're going to end up having to combine those when you add or subtract the top. Okay, so for this one, we have sine x. So this one I'm going to multiply out. So I'm going to multiply this in here. So sine x times 1 is sine x. Sine x times sine x is minus sine squared x. And then the bottom, again, I'm just going to leave it as cosine x times 1 minus sine x. Because what's going to end up happening is we're going to combine the top. Okay, so we're going to combine these. So they need to be multiplied out. And then we're going to cross out common factors top to bottom. So you don't want your denominator to not be factored. Okay, you want it to stay factored so you can cross out common factors. Okay, so then the top, we end up with cosine squared x, and then you're subtracting this whole top piece over here. So I'm just going to write this out so you can kind of see this happening. But when we have common denominators, we just subtract the tops when the bottoms are the same. So we have this whole thing over this one denominator of cosine times 1 minus sine. And then you just got to be careful here because you want to distribute this negative in, right? So we want to distribute this negative. So then this is going to be negative sine. And then this is going to be a plus sine squared. Okay, so we're going to do the top. We're going to end up with cosine squared x minus sine x plus sine squared of x. And we still have that denominator of cosine x times 1 minus sine x. Then if you remember, we see this cosine squared and we see a plus sine squared. So this is a Pythagorean identity, right? That cosine squared plus sine squared is always equal to 1. So where we see a sine squared and a cosine squared, we can plug in a 1. So instead of sine squared, cosine squared, we will replace those with 1. And I'm just going to write the 1 first. So 1 minus, just sine x. And then over cosine x times 1 minus sine x. And hopefully now you start to see why we left the denominator factor, because now our top, if we want to write it as a factor, it's really 1 times this factor, right? And we see that we have this factor of 1 minus sine x on the top and the bottom. So those are going to divide to 1. So we'll be left with 1 over cosine x, which is the reciprocal of secant. Example 9, now we've got an equal sign, okay? So now we're getting into equations, and this is on page 27 in your packet. But now we're getting into equations, so we're actually going to do more than just factor. We're going to end up solving using our unit circle. So in order to do this, okay, we need everything on one side of the equal sign because we see a squared function and a non-squared function. Now they're different functions, so we're going to have to deal with that in a little bit. But let's get everything to one side of the equation first. So we're going to subtract 2 from both sides and subtract cosine of x from both sides. So we're going to get 2 sine squared x, and then I'm going to just write the cosine next. So minus cosine x, and then minus 2, and then equals 0. Just going to move this down off that line. Okay, so now when we have a squared function and a non-squared function, and they're different, okay, we want to rewrite this so we have the same function so that we can factor. So if we look to our Pythagorean identities, that deals with sine squared, or that has a sine squared in it. Remember that that's sine squared plus cosine squared equals 1. And we want the sine by itself, right? So we can plug it in. So we're going to subtract cosine squared from both sides. So we end up with sine squared of x equals 1 minus cosine squared. So instead of sine squared, we can plug in 1 minus cosine squared. So be careful of this 2 out here, right? And then you're going to plug in 1 minus sine squared, or sorry, 1 minus cosine squared. So make sure you get a parenthesis around that because you need to plug that whole thing in and you need to double it. So now we'll distribute the 2. So we'll have 2 minus 2 cosine squared of x minus cosine of x minus 2. And then I'm just going to combine the 2's, right? So 2 minus 2 is 0, so that's going to be gone. So we have negative 2 cosine squared of x minus cosine of x equals 0. So now we can factor this. And because both these are negative, I'm going to take out a negative. And then I see a cosine in each, so I'm going to take out a negative cosine. So when I take out a negative cosine from negative 2 cosine squared, I'm left with positive 2 cosine. Negative cosine divided by negative cosine is positive 1. And then that equals 0. So now that we have 2 expressions multiplied by each other equal to 0, we can split them and set them both equal to 0. So if negative cosine of x equals 0, that would be a solution. Or if 2 cosine of x plus 1 equals 0, that would be a solution. So in this case, we'll just divide by negative 1. So we just want to figure out where cosine of x equals 0. And we're just going to do this on an interval of 0 to 2 pi. And then here we would subtract 1 from both sides and then divide by 2. So we also want to find out where does cosine equal negative 1/2. So remember that on your unit circle, cosine is your x. So we're looking for where the x is 0 from 0 to 2 pi. So that's at pi over 2 and at 3 pi over 2. So that will be 2 of our solutions. And then when does cosine equal negative 1/2? So when is the x value negative 1/2? And that's going to be here and here. And that's at 2 pi over 3 and 4 pi over 3 on your unit circle. So then those are all the solutions from 0 to 2 pi that will make this equation true. Example 10, very similar to the last one in the starting, except for that we have all the same function this time. So we've got the sine squared and the sine. Now this time we've got a squared version of sine, a regular sine, and then a constant. So we're going to be factoring this. And in this case, our a value is 2. So if you want to do this in the box, you can. I'm not going to. So I'm just going to know that 2 sine, the only way we can get that is by multiplying a 2 sine times a 1 sine. Okay, and the only way we can get 1 at the end is that if the end is 1. So now we just have to decide which one needs to be negative to get us a negative sign in the middle. So when we do 2 times 1, we want that to be negative. So 2 sine times negative 1 gives us negative 2 sine. And then 1 times sine would give us a positive 1. So that would make our middle negative 1. And then we can just split these and solve. So 2 sine x plus 1 equals 0. And sine x minus 1 equals 0. So on this one, we would subtract 1 from both sides and divide by 2. And then here we would just add 1 to both sides. And then we'll want to go to our unit circle. And remember that our sign is the y coordinate. So we're looking for when the y is -1/2. And again, we are just going to be looking, from 0 to 2 pi. So when is the y coordinate when is the y coordinate -1/2? So the y coordinate is -1/2 here and here. So that's at 7 pi over 6 and 11 pi over 6. So here's your 7 pi over 6 and your 11 pi over 6. And then when does the y coordinate equal 1? And that's here only at pi over 2. So then those are your angles that would make this equation true. Number 11 is another factoring one. And so then this one has an a value of 6. So if you wanted to do this one in the box, you could. And so this one, I'm just going to simplify it by just pretending the cosines aren't there for a second. So I'm going to do it as 6x squared minus x minus 2. And I'm going to put this into the box. So we have 6x squared minus 1x minus 2. So we'll multiply the 6 and the 6x squared and the -2x squared together, and we get -12x squared. And then factors of -12x squared that add to -x are -4x and +3x. And then you can put these in the box however you want, whichever spaces you want there. And then take out a common factor on the top. So both 6 and 4 divide by 2. And then they each have at least one x. So we'll take an x out. So then 2x times 3x gives us 6x squared. 2x times -2 gives us -4x. 3x times 1 gives us 3x. And then 1 times -2 gives us that -2. So then that's how this factors, but remember, it's not an x, it's a cosine x. So 3 cosine of x minus 2 and 2 cosine of x plus 1 equals 0. So then we can split these and solve them. So 3 cosine x minus 2 equals 0. And then 2 cosine x plus 1 equals 0. So then we will go ahead and solve each of these. So 3 cosine x equals 2, and then cosine of x equals 2 over 3. And then here we have, we'd subtract 1 and then divide by 2. So then when we'll go to the unit circle. Now, this first one isn't on the unit circle, okay? So this isn't a unit circle value, so we'll deal with that in a second. But this next one is, so when does cosine equal -1/2? And again, we're just doing an interval from 0 to 2 pi. So cosine is -1/2 here and here at 2 pi over 3 and at 4 pi over 3. So there's 2 of our answers. So then this one we're going to need to do in our calculator, okay? So you're going to have to do the cosine inverse of 2/3. And so this is going to give you one of your values, okay? So if you type in cosine inverse and then make sure that you are in radian mode, because that's how the rest of our stuff is. So we want to do cosine inverse of 2/3, and you will get 0.84. radians. Now, then we got to figure out the other one because our calculator will only give us 0 to pi. So our calculator's now just told us this angle right here of 0.84. So now we want to find this same value down here. Okay, and so we know that this reference angle is 0.84. So this one is going to be negative 0.84, right? If we go into the fourth quadrant, we know when we go backwards that that's just going to be a negative version of the angle. But since we want to start at 0, okay, we're going to want to do the positive coterminal of this. So we're just going to add 2 pi to this so that we can be at the positive version of this. And so just add 2 pi to this and you get like 5.44. So 0.84 would be another angle, and then 5.44 would be another angle. So those are our answers to this one. Okay, number 12 then just has one function in it. And so for this one, we're looking, now we got to be careful because this has a double angle on the inside, okay? So we're just going to pretend that that's not there right now, and we'll deal with that in a second. So we want to figure out when does the tangent equal the square root of 3. And so remember, for tangent, you're going to get square root 3 if you had square root 3 over 2 divided by 1/2. And tangent is your y coordinate divided by your x coordinate. So when is your x 1/2 and your y square root 3 over 2? Okay, so we know that that's or both negative. So we know that that's happening at pi over 3, and then both would be negative, creating a positive root 3 here at 4 pi over 3. So those are our two solutions. Now, those are our two solutions to this 2x, okay, because that 2x was inside of there. Okay, so 2x equals the pi over 3, or 2x equals your 4 pi over 3. So now you just end up dividing by 2 to both sides. So we'll divide by 2. So then x equals pi over 6. Okay, or divide by 2 here, and x equals 4 pi over 6. And 4 over 6 simplifies to 2/3. So this will simplify to 2 pi over 3. And then number 13, again, a very similar thing here. Okay, so now we have this different angle in here. So we'll just ignore it for a second, and we'll figure out when does the sine equal 1/2 from 0 to 2 pi. So when is our y value 1/2? Okay, so here at pi over 6, and here at 5 pi over 6. So then we have, instead of x equals, right, we have x over 3 equals each of those. So now we have x over 3, and I'm just going to write it twice right now, equals each of these angles that we just came up with. So equals 5 pi over 6 and pi over 6. So now we'll just multiply by 3 to get x by itself. So we end up with x equals 15 pi over 6, which both of those divide by 3. So when we divide both by 3, we end up with 5 pi over 2. And then here we'll multiply by 3 to both sides, and we end up with x equals 3 pi over 6. 3 and 6 both divide by 2. Or sorry, both divide by 3, so we end up with pi over 2. So then our two answers are 5 pi over 2 and pi over 2.